All right, so following up on that question today, I'm going to be talking about meteoroid showers at the moon instead of the more global structure that we measured with LADI. And the theme of this whole presentation is going to be similar to Menelaus, that we can use airless bodies as very effective detectors for the interplanetary dust environment. So the types of particles that we're detecting are impact ejecta, and the way that that works is the Earth, we're all very familiar with meteor showers. These are streams of particles that come in and ablate through the thick atmosphere that Earth has, and they burn up and they create these wonderful meteors that you see. The moon is essentially exposed to the very same fluxes, except there's no atmosphere to ablate. Those meteoroids, they all impact the surface and they kick up these large ejecta plumes that we can then measure. They're typically categorized, these meteors, the sources, into two different groups. Menelaus did a really nice job describing the sporadics. The meteor showers are when a body releases material and it has orbital elements that are very similar to its parent body, and so it fills in kind of a tube-like structure, shown here, for example, for the Geminids. And if Earth intersects one of these nodes, then you get a meteor shower. If after a long amount of time or there's some dynamical perturbations that separate the particles from their parents, they are sufficiently randomized and they make up the sources that Menelaus was just describing, the helion, the antihelion, the apex, the toroidal. They all have their different parent bodies, and there's different distributions for each one of those. The way that we detect these impacts are with the Lunar Dust experiment that was on board the LADI mission from September 2013 until April 2014, so about 6 months. And the way it works is you have an impact at the surface, it generates this impact ejecta cloud, and then the LADI spacecraft flies through it, where our instrument is essentially like a bowl, kind of scooping it up, if you will. And the way that it works is a dust particle comes in at high velocity, high enough to completely impact ionize. It generates a plasma puff of ions and electrons. We have an electric field set up to pull the ions into an MCP. The electrons get pulled into this hemispherical target, and so we can either get one or two coincident signals for every single dust impact. The smallest detectable range grain size is 0.3 microns, and to get both signals, it's 0.7. This is a summary of the entire LDEX dataset throughout our mission, and this is the impact rate for those two different size cuts. This is for when we get a single waveform or a single detection, the ion signal, and this is when we get both signals. The key point here is that throughout the mission, we had a lot of variations, but there were some also very large incursions, specifically the Geminids, which is known to be one of the strongest meteoroid showers on Earth, and correspondingly, that lit up our impact rates in the strongest amount for LDEX at the moon. Globally, this is what we detected when you take all these impact rates and you put it into the frame of where the sun is fixed to the left, and this is the moon's motion with respect to the sun, if we forget about Earth for a moment. And as Menelaus was showing, that what we saw was it was a lot more dense at the RAM direction, or the apex direction. We saw very few impact ejecta particles in the anti-apex direction, and there was a slight cant. It was slightly shifted towards the helion direction. The way that we've been understanding this is that just like at Earth, there's these three different sources, and if you add them up in a nice, simple way, then we're able to reasonably reproduce the structure with these three sources that we know in the equatorial plane. Again, the helion, the antihelion, and the apex. That's the global structure, but today we're going to be focusing on more of fine structure. And throughout the mission, what we noticed is usually we had impact rates of 1, 2 a minute, and every once in a while we would get what we called bursts, where this is the impact rate. All of a sudden it went from 1 to 2 to 3 to 10 or 100, and this is actually a binning thing. If you were to make this bin smaller, the impact rate's actually more like 1,000 per minute for a very short amount of time. And our best guess, especially due to the structure, is that we're actually flying through a very dense ejecta plume, where, shown in this cartoon, we have the trajectory of this really big ejecta plume that's been expanding, and we caught it just at the right time that we actually sometimes see the leading edge and the trailing edge. it turns out that during the Geminids, not only did we get the highest impact rate, we got the highest rate of these bursts. And what we could do is, if you look at the locations of all the bursts at the moon, shown in all these little dots, we were actually able to back out the directionality of the meteoroid shower for the Geminids just based on the locations that we detected this on the surface. So, for example, these are the locations of all the bursts, and if you just take each burst and you draw a vector out, and that's shown here in right ascension and declination, which is how we typically identify meteoroids. If you take all the plumes, we get an estimate. This box is the estimate for where the meteoroid shower came from. The X is where it actually did. And if we constrain to just the most dense plumes, it turns out within 1 sigma, we're actually able to tell you where the meteoroid shower came from at the moon. Now, we already have a very complex system of radar and visual measurements at the moon, so of course this is not learning anything new about the directionality of the Geminids at Earth. But now imagine, what if we had this at somewhere near Mars, or somewhere where we don't have a complex ground system of radar measurements and visual measurements? You could use this as a method to learn about the meteoroid environment of that either parent body or that heliocentric distance. So if we zoom in and look at just a few days around the Geminids, now this is kind of like impact rate. This is the surface density of the impact ejecta. It's a derived quantity from our measurements that essentially is the density of dust ejecta at the moon. And so this is a little cartoon showing, again, the Geminids hit from this direction. This is the same color bars we were previously looking at, and you can just see that the Geminids lit up that side of the moon. And now this is shown as a function of time and local time, where this dotted line is the local time that the Geminids hit. It's about 2, and it corresponds to that arrow. And what you can notice, there's a couple times that we were off. The LDEX instrument was off for operational reasons. And there's other spaces where we were either off or we just didn't detect enough hits, especially in the anti-apex direction. But now I want to focus on this slice out that's just the local time centered around the Geminids. And what we found was that the Geminids actually had a double peak structure. So fortunately, the off time, one of the off time did not capture this where we see fine structure. It did happen to center around the peak. But if you look at the shape of this profile, it actually had some significant fine structure. And this is still an open topic in the meteor community about what is the structure of this meteoroid shower, and then how does it correspond to the formation. For example, there's a paper by Zygo et al. Where they do see a double structure in radar measurements. There's a lot of different ways that the stream has been measured, and I think they're reaching consensus will take as many possible measurements that we can get. Typically, we've been using visual and radar, but now this is kind of a third tier that we can use to probe the structure of a meteoroid shower. This is an impact ejecta from an airless body. If we look at this in the heliocentric coordinates, this is, again, because we were able to get these nice exponential fits, we could see this is the first peak and this is the second peak, just split them apart. There's a theory about the formation of the parent body of this stream. So the Geminids, the mass of the Geminid stream is anywhere from 1/10 to 10 times the mass of its parent body, which means that it probably formed in a particularly violent event. And there's a model that says if this formed very quickly, say on a close flyby near the sun, the material ejected before it reached perihelion, pre-perihelion, and post-perihelion might evolve differently and form this tail kind of structure, this double peak. And the widths of these peaks and the separation of the peaks will actually inform you about the formation of this stream, which is the parent body we think is Phaethon. And I'd point out that this is the upcoming target for the Destiny Plus mission. And so this is a really neat way in which we can probe and possibly understand formation mechanisms about a stream or a parent body by using impact ejecta from the lunar surface. Now, so this is very, very fine structure, but the kind of bigger picture is that we could use these airless bodies to kind of sense the meteoroid environment throughout the solar system. So fortunately, the formation of the solar system has placed all these little breadcrumbs, all these little airless bodies throughout many different heliocentric distances, and we can use that to probe the environment. So at Earth, we have a ground network, and we have the moon. We have a lot of information. There's been a lot of groundbreaking work from the Messenger mission by Rosemary and by Peter Corney and Menelaus and many others, understanding the Ejecta environment using the neutral species. But once you go past the moon, it's a lot more difficult and challenging to understand the meteoroid environment. And there are all these nice little efficient ejecta sources. At Mars, you have Phobos and Deimos. You have asteroids that are all throughout. And then you have the Trojans all the way out at 5 AU. These all serve as very efficient probes to the dust environment. So as a last note, I'd say that, well, what can we learn even with one flyby? So for example, if we take what we learned at the moon and we just make a direct analog to an asteroid at 1 AU, this is the structure that we would expect. It's kind of like a lily pad. And the only difference between this and the moon, really, in the structure, is that the moon had an altitude dependence we empirically determined was exponential, but asteroids, since they're so small, would usually typically have like Coulomb's law scaling, just 1 over r squared. And so if we were to do even a simple flyby at some direction, this is a 45-degree angle, depending on where you fly by, either on the leading side or the trailing side, and how far you are, even with one simple impact rate profile, that information encodes the various strengths of the helion, the anti-helion, and the apex source, just with one line out. It's almost like a Langmuir probe, but for the meteoroid environment. And not only that, but even with one flyby, if you had a dust detector with chemical sensing composition, we could tell you the chemical composition of the surface without even landing. You're actually directly sampling the particles, because the impact ejecta are the surface particles that are ejected from the parent body. And so there's just an incredible amount of information being constantly sprayed out from these airless bodies that, as of yet, are a fairly untapped resource for planetary exploration. So in conclusion, we have gotten very high resolution observations of lunar ejecta during the Geminids meteoroid shower, which possibly informs us on the formation of the parent body and of the stream. These meteoroid processes are both a scientific resource for the meteoroid environment in general and for hazards, because if you have astronauts exploring on Phobos and Deimos, you need to know when they need to hide if it's going to rain more rocks that day. And airless bodies throughout the entire solar system are very efficient at creating these impact ejecta, and future missions could really characterize both the dust environment and the chemical composition of those bodies. So thank you.
Jamey, my question was, is the the altitude profile of the ejecta, does it depend on the impactor velocity, and can we tell something about the distribution of impactor velocities from ejecta measurements?
So that's something we looked at in the first cut. We kind of assumed a simple, just 200-kilometer scale height. There might be statistics that had big error bars. There might be statistics to actually show that scale height does vary. I would expect it should vary a little bit with impact velocity. For example, the apex should be more energetic. But I think that's something we should continue to push on.
Your discussion at the end about using near-Earth objects and sampling them from a distance is really exciting. Can we learn anything from the dust detectors we have had, let's say on Galileo, or I don't know if NEAR had a dust detector, because they did make close encounters and there might be some information there. What do we have in the existing database?
So from Galileo, we learned a lot. We learned a lot about the impact ejecta environments and how they scale from the icy moons of Jupiter. One of the interesting dilemmas is that when we went to the moon, we actually found out it scales completely different from when we measured the icy moons at Galileo. And so I think there's a big open question on how dust ejecta scales and the formation and how it depends on the impact velocities in the incoming distributions.
Oh, I'm sorry. Yeah, the Galileo moons are cool, but I was thinking more of Gaspra and Ida, because we flew by those with Galileo.
So that I don't know, but I can tell you that Galileo DDS did not have chemical sensing composition capability.
But well, we can talk offline.
Sure.
Yeah.
All right, save any more questions for our discussion section, which is after the next talk.